Good morning, everyone. I think it's Wednesday. Let's see. Today we are going to be covering some more root locus. Although on Monday we pretty much covered all of the technical stuff. All right, that was a good one. We pretty much covered all the technical stuff on Monday, so let's take a quick recap as I remember to share the PowerPoint with you. So what have we got so far? We found out how the open loop poles and zero locations tell us about the closed loop pole locations in class 1. We found out what parts of the real axis can be possible closed loop pole locations in class 2. We found out at what angle the closed loop poles that go off the page have to go as k gets large in class 2. And then in class 3, we did these three. And just to remind you, angles of departure are at what angle do the branches leave the complex conjugate open loop poles, and the arrivals are at what angle do the root locus branches arrive at the complex conjugate open loop zeros. The imaginary axis crossover points are exactly what you would think they are. They are the points on the imaginary axis where the root locus branch crosses from one side to the other, either left to right or sometimes right to left. The breakaway and break-in points are both points on the real axis where the root locus branches either leave the real axis because they run into each other and they have to become then complex, or a breakaway point is when the complex conjugate branches break into the real axis and then head their separate ways left and right. So I guess we should pause here and ask if there are any questions. Today's going to be pretty slow class. We're going to do you're going to do a lot of example problems, and then we're going to check our understanding. So I'm not super worried about talking fast today.
Really quick, just to clarify, correct me if I'm wrong, but the asymptotes are for when k is very large, like giving us an indication of where the trajectory of closed loop poles will be located. And then the angles of departure in our example are just where that starts, how it goes from what we found 18 degrees, and then eventually makes its way to be an asymptote of 60 degrees.
That's exactly right, yeah.
And then how do the asymptotes, because we had to find 3, we had to find 2 that were at 60 degrees and 1 that was at 180.
Yeah.
And so how are they different? How are they the same or similar?
Sure. So let's go to that slide. Let's see if I can find it. There we go, that slide. So an asymptote, regardless of what angle it lies at, tells you the behavior of a closed loop pole as k gets very large. Or I'll commonly just abbreviate that as it'll tell you what the branch does as k gets large. So we've got 3 branches that have to go to infinity, which is the technical term, or off the page is the phrase I've been using. 2 of them will go, well, one will go at positive 60, one will go at negative 60, and one will end up at negative 180 degrees with respect to the positive real direction. And of course, those angles are all rooted at the center of mass. Now, the 180 degree asymptote is unique amongst the 3 that we calculated in this problem. And that is, in addition to being an asymptote, it is the exact line on which the branch travels to infinity. So I'm talking about this as both an asymptote and a branch. They are coincident. And that's not true for the other 2 asymptotes. It doesn't have to be true in general, but it can be true, as we've seen here.
Got it. Okay, thank you.
Yeah, you're welcome. Let's go to the very last procedure. And this really is a recipe at this point, right? I'm pretty much telling you do 1, then 2, then 3, then 4, then 5, then 6, and 7. There are some caveats. There are some times when you don't need to do, say, step 3 or say step 4. But if you at least go through this list and check off the boxes, you'll have a reasonable root locus diagram. The last step is not technical at all. And it is because you have gotten everything you can get that is technically true. That is, we have covered all of the little peepholes into this cloud of mystery surrounding the pole locations. So what's left is an educated guess. And I'm giving that a bit more of a formal name here. This is filling in the gaps. We have basically just glimpses of the root locus branches, but we also know that the branches themselves have to be continuous curves. There's a theorem from complex analysis that says that if you vary the coefficients of a polynomial continuously, you will vary the root locations continuously. That is, if I smoothly vary k, then I won't have a root location that jumps from here to there. It has to travel continuously. So we don't have a continuous curve. We have bits and pieces that we now have to bring together. We have to connect the dots, as it were. And this is, in my experience, this is the most uncomfortable step for students, because the other ones, like, as long as you can read what I've written on the slides, you can do those things. This step is much more adventurous. But the good news is you can't go too wrong. Basically, my abiding rule is simpler is better. So if you know that one branch has to get from A to B, just do your best to connect A to B. The more of these diagrams you do, and the more that you either simulate or draw on your own, the better sense you'll have for what the curves will look like. So let's actually conclude this problem, this example problem. What we have on the screen now is all of the points. So I guess to recap, let's go in orange. We first figured out the open loop P's and Z's. So that was the orange X's and O's here on the screen. Then we did the real axis. That gave us this bit and that bit. Then we did, the asymptotes. That gave us the fact that the branches have to end up at these angles, and there's an angle here, but we already knew that because the real axis exercise. Then we did the angle of departure, which told us this little bit. There were no angles of arrival because there were no open loop conjugate zeros. Then we did the imaginary axis crossing, which gave us these 2 points, plus or minus 2.28j. And then we did the break analysis, break away or break in, and that told us that there were none. So I can't actually draw an arrow to that because we showed that there weren't any breakaway or break-in points. And so we are now at step 7, which is do your best. So what is going on here? I have to connect this branch through this point to get to this slope. And so usually I do this on a chalkboard, which I've gotten reasonably proficient at, but this is the first time on a tablet. So I got to go through that line, that point, and that's not great. I tell you to do your best, and then I give you that. Let's go there. Yeah, I like that. So now I got to do my best to mirror that down here. So I crossed over. And that's not great. So once you draw the top half, that actually governs how you draw the bottom half, because these have to be mirror images of each other. Okay. That, I believe, is what I would turn in for my root locus diagram. So again, what have we shown here? The red branches, the big, thick, red splotches of ink, are the possible closed loop pole locations. Lovely. All right, where was I? The big red splotches here are the possible closed loop pole locations as K increases. So you'll sometimes often see extra little arrowheads placed here, just to tell people that you know what direction the poles are moving, and these arrowheads are almost always drawn as K increases. Okay. So are there any questions about what just happened? Because I do my best to say you got to just fill in the blanks.
So you're saying is we trace the pole locations as they approach the asymptotes?
Yeah, that's what I just did. Yeah.
Okay, as our final root locus diagram.
Yeah, here you have it. There's nothing more to do. So what could we use this diagram for? Well, clearly it tells us where the closed loop poles locations could be as K goes from 0 to infinity. But if you take that statement and flip it around, it also tells you where the closed loop poles can't be for any positive K, right? If you, for whatever reason, need a closed loop pole here, you're out of luck with this design, with this controller. If you need them here, you're out of luck. So I think that a lot of attention is paid to the branches, as they should be. But what's actually sometimes more important is where the branches are not. And it tells you where you can't have closed loop poles. So go ahead.
You said when you say closed loop pole, is that referring to only unity gain or to all variations to the to a feedback loop?
So this example was all based on this system. And so there were a lot of things that were chosen for us before we even set foot into this example. In particular, everything was chosen for us, including the controller form, the plant form, and the feedback form. The only thing that we were left to vary is this open loop gain K. And so that's the thing that's changing, that's causing the closed loop poles to move. Did that answer your question?
Yeah.
Okay.
I would have a question.
Yes.
On the last slide, can you explain again why the poles cross the asymptotes and not stay on one side?
So that is actually, I'm not actually sure about that. I do know that the imaginary axis crossing that we calculated, about 2.28, that actually lies below the line that's rooted at -4/3 and goes up at 60 degrees. And so I think I did the trig before class, and this this point where the asymptote crosses the imaginary axis is higher than 2.28. And so that tells me that the branch starts above the asymptote, but eventually has to go below the asymptote because that's where it crosses the imaginary axis.
Okay, yeah.
Yeah, so that's asymptotes, again, they only govern behavior at large K, which means that technically speaking, crazy stuff could happen down here, and the asymptotes are only relevant very, very far away.
All right, thank you.
Yeah, good question.
So we started this question with the assumption that there's just a single feedback gain or there's just a single gain of K that's changing it. Could it work with other, I guess, other variations of that? Does it have to be just a single gain?
That is a great question. So you're already starting to see the limitations of this method, that what I taught you only works as K varies. Now I'm going to teach you in a day or two how to adapt this method so that you can do it for a different single parameter as it varies. Say, if the 3 were a variable and the K were fixed, we'll learn how to use the stuff that we've just learned in that situation. It's not directly applicable, but you can massage it and we'll get there. Now, probably what you're asking is, what if I have both a variable K and a variable pole here? And that is a significant limitation of root locus design. Because these curves turn into areas, right? So these lines, curves, lines, whatever, are one-dimensional objects, right? They have no mathematical thickness, they just have length. Once you start varying 2 parameters, then all of a sudden that introduces a width, a non-zero width to these, and they become 2-dimensional. And then we're trying to get 2-dimensional areas on a 2-dimensional plane, and all of the rules I told you just completely go out the window. So root locus is good if you have one parameter that you can vary continuously, and I'll go one further than that. If you have, say, discrete points that another parameter can be, then you can iterate. Then you can do this for those multiple discrete points. So what I would do maybe is, if I had the option to move this pole, so remember the controller was k over s plus 3. So if we had another controller on the shelf that we could use that had something like this, then actually what I'd like you to be able to do by the end of this unit is predict how the root locus will change if we swap from one to the other. We're still varying the open loop gain, but now we're changing one of the open loop pole locations. And that, honestly, is why we still teach root locus, is for you to get the instinct to be able to predict how a given root locus diagram will change if I change some of the parameters.
If we're given this in the problem statement that it's going to change, would it be good to solve it algebraically with something like a in place of 10 and just like try to see as far as you can get, or would it be better just to do each from scratch?
The first couple times you do it, go ahead and leave it as an unknown, but you're going to run into then, once you leave any of the open loop poles as variables, your center of mass is going to be a variable, your angle of departure is going to be not a variable, but a function of that variable. Your angle of departure will be a function of the variable. What else would change?
I see.
Certainly the imaginary axis crossing would be like a heinous function of that variable. So if at all possible, don't. But if it helps you kind of step from here to there, go for it. But I think that we're getting a little bit ahead of ourselves. Before we can use root locus, before we can determine how a root locus diagram will change, we should probably get some experience with like actually drawing root locus diagrams. That's crawling before you can run, I suppose. So my challenge to you is I would like you to get as far as you can on this problem. So I'm on the third to last slide, and I would like you to sketch the root locus diagram for this system as k varies from 0 to infinity. I'm going to give you 8 minutes. I will be here, I will be muted, but I will be here, and I will be available to help. In the meantime, I'm probably going to go find the chat window. But yeah, this is time for you to practice, see what you've learned. All right, that was just about 8 minutes. So if you're still working, of course, can't see you, so keep working. But I'm going to try and catch up. Maybe before I do that, are there any questions? Anyone run into trouble that they'd like help with now before I get to it?
I got complex roots in the denominator. I don't know if I did something wrong.
Could you say the first part again? I didn't hear.
I said that I got complex roots for denominator.
Yeah, so I think you're
S
going to
squared.
get poles open loop poles at -1 plus or minus j. You talking about this guy?
Yeah, that was wrong.
Yeah, so anytime you run into a polynomial that you're not sure that you can factor, if that polynomial has like fixed coefficients, say 1, 2, and 2 in this case, go ahead and use a calculator, go ahead and use a computer. I think a lot of students worry what polynomials I want them to draw and what polynomials that are okay to check with a computer. And so the rule for my class is if you have fixed coefficients, so 1, 2, 2, use a calculator. If you've got variables in your coefficients, then use something more sophisticated like Roth-Hurwitz or locus or something like that. But yeah, I think so step 1 is draw the open loop poles and open loop zeros. And so we've got open loop poles at -1 plus and minus j. And we've got open loop zeros, one of them at the origin and one of them at -4. So I guess incumbent on us is to remember that the open loop transfer function is the product of all the blocks around the loop. So this is k times s plus 4 times s over s squared plus 2s plus 2. Okay, so step 2 is determine the parts of the real axis that are in the root locus. So actually, let's throw those out to the class. Who can tell me what parts of the real axis belong to the root locus?
It's all the area between the two zeros, right?
That's right. So if I am out to the right, then I have an even number of x's and o's to my right, so that can't be in. And once I cross the origin, I've got one thing to my right, which that is then in. Once I cross -1, I go from one thing to the right to 3 things to the right, which is still odd. And so that still holds true anywhere in here. Good. And then it holds false if I go out here. So yeah, the only part of the real axis that is in is between -4 and the origin. So here's the first curveball. How should I figure the asymptotes?
Sorry, Dr. Markel, could you explain that one more time? You said something about like odd area on the real axis. Could you explain that one more time?
I'm just going by this rule that we have back here on slide 9.
Oh, gotcha. Okay.
Yeah. Okay, so asymptotes. What's the curveball, and how did you get around it? Maybe we don't have any baseball aficionados. I think the curveball is if you go to work out the asymptotes, you get sum of the p's minus the sum of the z's over n minus m. What is n minus m in this case? 0. So the workaround is there are no asymptotes. This is unnecessary. There are 2 open loop poles. There are 2 open loop zeros. That means that there are 2 closed loop poles. Those closed loop poles will travel from the x's to the o's, and they'll never go off the page. Okay, so in this particular example, there are no asymptotes to calculate. So we get to skip step 3. For the departure angle, first off, do we need to calculate the departure angle? What do you think?
No.
Try again.
Oh, JK, take it back.
Okay. Yeah, just kidding, right? There are complex conjugate open loop poles, so we have to depart from them. So let's cook up the formula here. This is 180 minus the angles of the vectors drawn from the other open loop pole, singular in this case, to the open loop pole we're departing. So let's get some other color in here. No, that's my, yeah. So this is a 90-degree angle. And then we're gonna add gamma 1 plus gamma 2. Right, these are the vectors rooted at the open loop zeros pointing to the pole that we're departing. So what is gamma 1? That's going to be 90 degrees plus 45 degrees. So we'll call that a $135. Gamma 2, that is the angle whose tangent is 1/3. So this is inverse tan of 1/3. So we've got all the pieces that we need there, except for how to work the arctangent of 1/3. But go ahead and use the calculator to tell you that this is going to be approximately 243 degrees. So let's get our root locus blue here. 243 degrees. That is not quite 270, but it's certainly more than 180. So it looks like something like that. Maybe I could be a little bit more clear by not adding an arrowhead in there. So sure, that's about 243 degrees. Remember, we're measuring from the real axis counterclockwise, just like you would for phasors, just like you would for normal complex numbers. The policy of using the negative real axis to measure beta angles holds only for that canonical form. That's the only case that I've ever seen it used. All other angles are kind of standard with respect to the due east. Okay, so if we've got the departure from the north half plane complex conjugate open loop pole, we can mirror that to the southern half plane. Questions on that?
Yeah, how do we find those angles again?
Which angles? To which angles are you referring?
The 135 and the tangent, arctangent of 1/3.
Those are the angles formed by the vectors. Let me see if I can find the slide. Here we go. They are the angles formed by the vectors rooted at the open loop zeros. So here we only had one, so it was gamma 1, pointing to the open loop pole that we're departing. And in the example now, there are two open loop zeros. And so the angle from here to here is gamma 1. And the angle from here to here is gamma 2. I guess, I don't know how better to say that. This is 135 degrees. This is 18 degrees. Okay, sweet. So step 4 is done. Step 5, imaginary axis crossings. Needed or not needed? Because if we can skip it, I'd love to skip it.
Yeah, I think we can skip it.
I agree. Based on what we have so far, we know that the branches are going to leave these x's and basically head left and towards the real axis. And they're always going to then live on the real axis in the negative half plane, or in the left half plane. So I think that there is unlikely any imaginary axis crossings.
How do you know if it's going to go to like, I mean, I guess we know the angle it departs at, but how do we know it's not going to go to like the right zero?
So yeah, so this is why I have to say unlikely, because we actually haven't shown that it can't be this. But we do know that whatever the top one does, the bottom one will also do. So they both can't go to the zero. So they can't come, what can't happen is that. That's impossible, because we know that the top has to mirror the bottom and vice versa. And they both can't end up at this open loop zero, because one of them has to go to the other open loop zero. So we know that there has to be a breakpoint here somewhere. And that breakpoint has to be in the left half plane, because that's the only part of the real axis that is a valid root locus branch. So yeah, barring any kind of super crazy wiggle here, which I am going to go ahead and say not going to happen. And that's based on experience, which maybe you don't have. I'm going to go ahead and confidently skip the imaginary axis crossing and hope that it works out. That's kind of a weird way to say it. But I think that brings us to step 6, which is our break in or break away points. So in this case, it'll be a break in, because we have branches that are off the real axis that need to get onto the real axis. Connor, do you want to ask a question?
Yeah, you said that a pole has to go to a single zero, correct?
One pole, one zero.
Okay, so eventually those two will go different directions.
Exactly right. So yeah, let me finish the break-in analysis, and then I think it'll become more clear.
Okay, thank you.
Sure. So break-in point. This one, we need to identify the numerator of the open loop transfer function, which is s squared plus 4s, and the denominator, which is s squared plus 2s plus 2. Then if we differentiate these, we get 2s plus 4 and 2s plus 2. And then we solve s squared plus 2s plus 2 times 2s plus 4 minus s squared plus 4s plus nothing times 2s plus 2 equals 0. This on its face looks like a third order polynomial. It turns out that you're going to get an s. I think the s to the 3's will cancel. Yeah, so I get 2 s to the 3's over here, and I get negative 2 s to the 3's over there. So technically speaking, you could use quadratic formula for this, because it looks third order, but it's actually second order because the third order components will cancel. But go ahead and use your favorite root finding method here. I use quadratic formula, and I got 1 plus or minus root 20 over 2. So we only expect one breakpoint. Which of the two do you think we should use?
The minus?
I think so. I think we want the 1 minus. So what would this be? 4 goes into 20, so let's pull out, this is 1 minus root 5. Yeah, I think that's true. Because 1 minus root 5 is a negative number, and we need the break-in point to be a negative real number. If you were to pick 1 plus root 5, that would put us somewhere over here, which is not valid. So let's work this out. This is approximately negative 1.2. And so what we've just shown is that there is a break-in right about here. Okay, so that was all 6 of the knowable, calculatable root locus glimpses that we get. What comes next is artistic license. There's not a whole lot of room here for license, but I'm just going to connect that to that and then down there. The closed loop poles will travel from the x's to the o's, which means one of them is going to head left to the open loop 0 at -4, and one of them is going to head right to the open loop 0 at the origin. Connor, I hope that was what answered your question.
So will this one just so happen to break in at around the center of mass because there's only 4 of them?
So the center of mass is undefined here because the center of mass, you're dividing by 0.
Oh, okay.
Can I ask?
Ernie, what do you got?
Oh, so obviously there's going to be a break-in point at -1.24, and because both poles meet at that point, do we, I guess in a way, do we really care like which poles go where, or it's just relative to their positioning of what the closed loop pole could be when you put a gain to it?
I smile because every single time I teach this topic, someone asks that question. And
I was just curious.
no, I don't. The answer is we don't care whether it's this pole that goes left or right. And because mathematically, once they're right on top of each other, the poles are indistinguishable, which means that we don't actually know which one came from the top and which one came from the bottom. But yeah, I guess there's some like, you want to be able to track your poles, like you want to put name tags on them, but that's not important or possible, I guess.
Is it possible in MATLAB? I'm just kidding. Never mind.
No, because once the poles are coincident, then like there's no history to them. Right? If I were to give you this problem starting with the poles coincident at -1.2, you wouldn't know where they came from. So you wouldn't know which one to send left and which one to send right. So it's not possible. And it's not just me holding something back from you. It's not mathematically possible.
I know it's there, but could you like show maybe a little better the departure angle in the nicest way possible? Totally great diagram. Love it.
So show what the departure angle is, or show how I calculated it?
How it go on the diagram, the finished part that we just drew. where is that 243?
So we got the departure angle is this angle, 243 degrees.
Awesome. Thank you.
You're welcome.
And once the holes come on the real axis, right? Do they, once they go towards the holes, they like, I know that's their like limit. Do they just like sit there and like fill up those holes, or like what's the point basically? That's what I'm asking. What
So
happens
there
in the
is,
end?
so for any finite gain k, the closed loop poles will be somewhere on the blue lines, and they only get to the open loop zeros as k, if k is infinite. So for any practical engineering purpose, your k is going to be finite, which means your closed loop poles will be getting possibly close to the open loop zeros, but they won't ever actually fill the holes there. So
Okay.
yeah, I mean, if you're asking why I didn't shade all the way to -4, it's mostly because I don't know. I like to have the O's being distinct. But strictly speaking, like really these locations, this 0 and -4, are the asymptotic location of the closed loop poles as k goes to infinity. I hesitate to use that word because they're not the asymptotes that I taught before, but they are the limit points. I think that's probably a better phrase. They are the limiting points of these two branches.
I understand that. Okay, thank you.
Sure.
One last question. In general, I know that the departure angle is like a starting point, and asymptotes are the ending point, and there's some transition that happens.
Sure.
But in this case, because we didn't have a center of mass, are the asymptotes, I guess, for this branch 0 and 180?
It's hard to say because the center of mass isn't defined.
Mm-hmm.
So to root the asymptotes anywhere, we can't actually root them anywhere. I don't think that's a necessarily correct or helpful way of thinking about this.
Great.
So I think probably maybe one thing that might be helpful is the fact that this angle, this incidence angle, has to be right. When you've got two branches breaking in or breaking away, that occurs orthogonal or perpendicular to the real axis. We haven't proved that, but that is it is true. So this is a 90 degree. So when you talk about angle of departure and then angle of quote unquote break in, we are going from a 243 degree angle to a 90 degree angle.
Okay, thank you.
Yeah. All right, so I have run overtime on the past several lectures, which means I owe you, and I'm going to stop here. So we'll do one more example next time, and then we'll close out Unit 5. But that should be a pretty smooth transition to Unit 6, which is basically the use of root locus diagrams. All right, everyone, I will see you in lab. Thank you.